Welcome back, everybody. So in the past couple of weeks, we have talked extensively about the monotone framework and how you can actually use it to implement intra-procedural flow-sensitive data flow analysis. And in this week, I want to talk a little bit more about two techniques that may allow you to implement such analysis, such that when they actually execute, they run more efficiently, but at the same time also retain a certain level of precision. And these techniques are called widening and narrowing, and that's what I want to cover in my presentation this week. So in order to discuss the related examples, I would like to get back to this interval analysis that we've already covered. And here we are assuming a slightly extended version of the interval lattice that I already showed you. But as I discussed before, the general idea is that we want to compute upper and lower bounds for integers. And yeah, this has a number of possible applications, right? So for instance, array bounds checking, which can be useful to detect buffer overflows in security, but also to choose some well-fitting integer representation in compiler optimization and so on. And in general, we have a lattice that looks like this. So we basically have intervals comprising of natural numbers, where the left-hand side value L is smaller or equal than the right-hand side value of H. And here we're actually using a lifted lattice, which I'll get back to in a second. And then the natural numbers that we're using here, well, they're actually not, I shouldn't have said natural numbers, they're actually whole numbers, right? So they include the negative numbers as well. And we also include minus infinity and infinity just as sentinels. So basically, you could say top elements. And then we have also intervals that are ordered by inclusion then, right? So this has to form a lattice, like I explained in the previous lectures. So for instance, we define this smaller equals relationship here in such a way that we are saying if we have such an interval here, it is smaller than this other one if basically it's included. So that means we have this value here, which is smaller equals than this lower value. And the other way around, this value here is smaller equals than this, this upper value. And if you do that, then you basically obtain a lattice that looks like this. So here we have basically the top element of our lattice, which is defined by the interval from minus infinity to plus infinity. Then we have all the different values in between. And for instance, we have a connection between this interval and that interval because this interval is wholly included in that interval here. And at the bottom, we have this bottom element here, which in this case we are interpreting as not an integer. So in general, we have a total lattice for the entire, sorry, for any program point that looks like this, right? So at any program point, we have a lattice L that maps individual variables to these intervals, right? So we have a map lattice that includes a mapping from variables to these intervals that we just defined. And this provides then bounds for each integer type variable. If we're using the work list solver that we discussed in the previous week with only the entry node, right? So that starts at the procedure's entry node and then iterates through the procedure, then it helps to use the lifted lattice because if we do that, then we can basically introduce an additional bottom element that lets us distinguish the following two situations. So if we have the bottom value of this lifted lattice, then this represents an unreachable program point, Whereas when we have the bottom value of L itself, that actually represents a program point that may be reachable, but where all variables are non-integer variables. It depends on your exact analysis requirements, whether you require that distinction or not. But if that is helpful to you, then by using this lifted lattice, you can get it. One important point, and that's really the important point for this lecture that I'm giving this week, is that as I discussed earlier already, also this interval lattice has an infinite height, right? Because you can have these infinitely increasing chains that go all the way, in this case, for instance, until 0 to positive infinity, and this chain is obviously infinitely long. And that is the problem that we want to address with these techniques, widening and narrowing, in this week. So let's look a little bit more into how the analysis is formally defined here, because that will allow us to denote also widening and narrowing a bit more formally as well. So in general, for the simple case, so where we don't have an assignment, the analysis value that is being computed for a given variable v is very simple. It's basically just the join of all the previous values that we had at the predecessors of the current statement, right? So we are accordingly to what was also defined in the MFP solution, we're getting all the predecessors' values and simply joining them together. When we do have an assignment statement with such an expression E on the right-hand side, it's basically the same expression except for the case that we replace the current value for X by a mapping where X now points to this right-hand side expression here. And that is an abstract evaluation of this input value join V that we also have here. And the expression then being applied to that input value, right? So we take whatever input value is valid before the current statement, we apply that expression to it, and then the result we associate with X within this map lattice. And this eval function that I just showed you, that is then an abstract evaluation. So for instance, you can define it as follows. So basically here, sigma is an environment, so a mapping from variables to concrete values, or no, actually not concrete, to abstract integer values that we are carrying around. And so if you want to evaluate a variable itself, you're getting the current variable's value by simply accessing the current mapping that exists for X in sigma. If we are evaluating an integer constant, it's rather simple. Then we are mapping this to the interval that only contains this integer constant. So it's bounded on both sides by the same constant value. And now this is the probably most interesting part here when we are evaluating over sigma an abstract operation op that is defined in the program on expressions E1 on the left-hand side and E2 on the right-hand side, then we are abstractly, so that's why there's this bar over here, abstractly evaluating this operator on the values of these expressions and the individual values for the left-hand side of this abstract operation and the right-hand side, we again recursively obtain by evaluating these sub-expressions over sigma. Okay, so we're evaluating these sub-expressions first, and then we're applying the abstract operation. And here, what's important is this abstract operation is not one on integers directly, but it's actually an abstract operation over intervals, right? Because this domain that we are operating on, it's the domain of interval values. And so this abstract operation is actually not quite trivial to implement. So I have formal definition of its properties here, but how exactly you need to implement it actually depends on the operation that you have here, right? So this could be any numeric operation like plus or minus or division and so on. And depending on what you have there, that might need to look a little bit different. But one possible definition that you can have here is the following. So you're basically defining new intervals again, and you're saying whatever the minimal value is of that operation here, where you take x out of this interval and y out of this interval, that should be the result for your left-hand side of the resulting interval here. And accordingly, the maximal value that you can get out of this, that should be the right-hand side value that forms the result, the resulting integer interval that you should get out of this operation. So here I won't go into too much detail about this because that's not the point of the current lecture, but you would have to define these abstract operations on the interval values. As I already discussed, the lattice has infinite height, so actually the fixed point algorithm as we discussed it, it does not really work, right? So I told you before, if you want to be able to compute the MFP solution, then you need to have the so-called ascending chain condition, which here we don't have. And so now you could say, well, then simply don't do it, right? Use another lattice. Yeah, I don't know. So for instance, use a bounded lattice, right? So you can try to restrict this to 32-bit integers. But that's also not a practical solution because also 32-bit integers are, that's a damn large space. And if you want to iterate or actually need to iterate 2 to the 32 times in order to finally eventually reach your top element, for instance, that's not practical at all. That will take a long time, and that's something that's not really helping you. So the whole problem is that if you are applying your fixed point iteration, so you're repeatedly applying your flow functions f to this vector, well, basically this lattice vector here, where this is the element for the first statement, this is the one for the second statement, and this is the one for the last, then this is not guaranteed to converge, right? And at home, you can think of an example program where this is happening, but in fact, we already discussed cases where this happens, right? So I think that's rather simple to see. And like I said, using just an arbitrary bound, such as 32-bit integers, that's also not really helping. So that's why this week we want to discuss a technique called widening that gives you some useful solution. Widening is defined through a so-called widening function. So let's introduce such a widening function omega, which is a function from such a vector to another vector that is defined as follows. So here the idea is that in every iteration, and really here I mean in every single iteration, we are not just applying f as previously, but we are also then applying omega right afterwards, right? So we are applying the flow function to every statement, and then we are applying the widening function to each result. And the idea is that this converges on a fixed point that is a safe approximation of each individual iterative result that we have obtained here. So the result of this should always be larger than the result of this for every value I that we have here. So that means the function omega that actually coarsens the analysis information. And you can think of this as turbocharging the iterations that you have through your lattice. So whereas you would normally have a fixed point iteration that looks like this, right? So we repeatedly apply f, and this may take a long time until then in the end maybe we reach the top element anyways. It just takes a long time. Um, Using omega, after each and every single iteration, we are applying omega, and this by construction is guaranteed to always bring us higher in the lattice, or actually at least as high as we currently are. But of course, the idea is that we actually get higher in the lattice so that we reach a safe approximation earlier than normally. And this omega function is defined pointwise on this lattice L to the n. So you could also say it's basically operating on each abstract value at every single statement. And this is actually parameterized with a finite set B, which are basically bounds that you have in the interval lattice here. And in this case, where we're talking about the interval lattice, it must actually contain minus infinity and also plus infinity, so that we can still retain the representation of the top element that covers this entire interval here. And typically then B is also seeded with all integer constants that are actually occurring in the given program. We will be discussing this later, but that can actually make sense. If you seed it this way, it basically means that you are allowed to define integer intervals that border the constants that are actually occurring in your program. And because the constants occur in the program, it's very likely, right, that they form bounds of such intervals. So this can be a sensible choice. And then the idea is to find the nearest enclosing allowed interval that is definable through these boundary elements in B. And basically, then if you have any such interval that covers the range from A to B, the widening of that interval is defined as follows. So you're taking the maximum value within B that is smaller than A to be the left-hand side bound, so the smaller bound. And you're taking the minimum value in B that is still larger than B as the right-hand side value, right? So you're restricting the interval to values from capital B, but they still have to adhere to this property, right? So the left-hand side must still be smaller than A, and the right-hand side value must still be larger than B, okay? And for bottom, you simply keep bottom. Now let's look at a concrete program and what this might look like. So what kind of program is this? What is it doing? Obviously, it's a contrived program, but it's useful to look at for the purpose of this widening example here. So y initially has constant value 0, and then we are iterating through this loop an arbitrary number of times, actually, because we assume that input is really an input value that we don't know anything about. And then in each and every single iteration, y is actually being increased by 1. Okay. At the same time, before the loop, the value x has the the variable x has the value 8. And then here, within each single loop iteration, it also obtains the constant value 8. Okay. So that after the loop has finished here at this program point, and that's our point of focus for this slide, we know that x definitely has the value 8. Okay. So at the beginning, we initialize using this mapping here, but then at this program point, actually, when processing the first iteration, we know that x is 8 for sure, and y points to this interval from 0 to 1, but then it points to the interval from 0 to 2, then 0 to 3, and so on. And that's now again showing this problem, right? So if you continue doing this, this can take a long time for you to reach any sensible bound that you might have defined in your interval lattice. So now the idea with widening is that you define such a domain of boundaries B, which, for instance, in this case, could look like this, right? So like I said, we take the integer constants that are part of the program, plus minus infinity and positive infinity, which gives us these values here, right? 0, 1, and 7, and the other boundaries. And so basically, you now have these natural numbers that you see down here. And now we have to see how do we replace these regular intervals here by their widened representations. And so, for instance, if we look at the interval from 8 to 8, then this basically falls here, right? So it's larger than 7 and it's smaller than infinity, of course. So now we are choosing the interval from 7 to infinity to represent that original interval here. So the interval from 7 to infinity is the widened abstract value that we use to represent the result at this program point. And what you can see here now is that this also immediately stabilizes, right? So this value never changes anymore, actually. But it is also obviously a little bit more, well, it's actually quite a bit more coarse-grained than the value that we had earlier, right? Because previously we knew that this had the constant value 8, and now we only know it's something between 7 and infinity. The positive effect of the widening you see on the right-hand side here, though, because if we do the same for y, then we will get the following intervals after widening. So at the beginning also here, y points to the interval from 0 to 1. So that's basically here. But then immediately in the next step, we jump to this widened interval from 0 to 7 here. Okay. And then immediately in the next step, we even jump to the widened interval from 0 to infinity. So that means only after 3 iterations, we have reached this value here, which then actually happens to be our fixed point, right? So after this, if you apply the flow function again, and the widening again also, you will obtain immediately the same result. So that means after 4 iterations in total, the analysis has finished. But as you see here, it is giving you a more coarse-grained result than what we saw earlier. Widening, it's an adaptation of the flow functions that we saw earlier. So you obviously have to wonder, is this actually correct what we are doing? Is this always still guaranteeing you a sound result? But in general, it works whenever your function w is an extensive function. So that means it's really defined on the entire lattice. And it's also monotone. And importantly, now w of L is a finite height lattice. So sorry, omega of L is a finite height lattice. That's the entire point, right? That this time we are really moving to something that is finite. And then we basically obtain this safety condition here, which is saying that compared to the normal value that we would compute in every single iteration, so for every I, we get the guarantee that if you apply omega afterwards, we do get a larger value, right? That's simply because F is monotone and W is monotone and also extensive. Then we also get the result that this combination of the two functions is also a monotone function. And so the fixed point always exists. And so very trivially, actually by definition, you can see that widening is actually correct. So it retains soundness and it's guaranteeing you to give, to get a sound result even after widening is applied. Yeah, that's what widening is all about. So it allows you to reach your fixed point earlier at the cost of potentially losing some precision. In the next video, I will be talking about a sort of mirroring technique called narrowing, which allows you to regain some of that precision. And that can also be used in combination with widening, which is often, of course, a very sensible combination then. I'll see you then.